one of my former students who runs his own business in Petaluma, and in fact is looking to hire some of you to be the sysadmin or sysadmins for his business. So you'll find out about that next week. Today I have the pleasure of introducing you Dr. Gummaraju from Advanced Micro Devices, and he will try to persuade you to switch to GPUs.
Should I wait for a couple of minutes or go ahead?
Dr. Ray Warner typically shows up in the next 5 minutes with some students.
Oh, okay. So, should I just go ahead or?
If you want to wait for her.
She said she might be.
Tell us some jokes while we're waiting.
I've got a question. How do you perceive, this is a side question, that's what I want to ask you. How do you perceive the emergence of ARM chips onto the market when they're new multi-core designs like Cortex A9 and A15?
Right. I think that's great. I wasn't sure what the background of people here is to start off with. So anyway, so I think ARM cores are, I think that they're a very interesting role because they have like really simple cores.
Yeah. So
that's why they consume really low power. So I think when it comes to mobile devices, they're probably going to have a big say in the marketplace. So that seems to be their forte so far. It's probably going to go ahead in the future. And I think recently our competitors, NVIDIA, teamed up with ARM, I guess, to come up with their more tablet-like devices. So I think that's going to create an interesting marketplace.
If they're making simple pipelines and you have a more complex pipeline, all of a sudden, if they're able to put more cores on their die, can they outbeat you by keeping a simpler pipeline?
So actually, the whole thing comes down to what kind of applications you want to run. Like if you're going to run simple applications, like maybe word processing or just browsing or stuff like that, then if you have more cores, you can run more number of these in parallel. Like you can run more browsers in parallel, more tabs in your browser in parallel, and it works great. But when you talk about any kind of applications that would probably need like performance, real performance, like if you want to do a simple example is GCC. If you want to compile your program using GCC or something, or do your development on that. So those kinds of things, these complex cores are much more capable compared to these simpler cores. So it will be like, I'm not sure it's going to be an order of magnitude faster, but it's going to be pretty close.
Well, GCC, I wouldn't see like floating point operations being done. Or what type of operations are you talking about that are more?
Well, I think there are two kinds of operations that are both going to be faster when you talk about complex cores. One is integer operations involved, like memory and things like, if they have a lot of branches, like, a lot of control flow in their programs, then you would need sophisticated pipelines to be able to not stall when it sees these kinds of behaviors. For those kinds of things, these kinds of processors are really good. The x86, like AMD and Intel processors. On the other side of things, if you have like floating point operations, what you're talking about, that again comes down to some of these applications, like I don't know, any kind of game processing or physics and these kinds of things. So they would need a lot of floating point units, and that's again where these kind of really little more complex cores play a big role. I think we'll cover parts of that in the talk. So
I'm sorry, one more follow-up. It doesn't matter. Is that okay? Have you ever heard of ParaVM, where it takes heterogeneous cores and with directives in the Java code, it actually can just-in-time compile per core for heterogeneous cores?
Oh no, actually that's actually very interesting because that's very related to what the research that I'm doing, but we do it at a different, like some of the language based more like on C than Java. So I think that's interesting. Hetero VM, you said?
Yeah, it's Hera, H-E-R-A-V-M.
Oh, Hera VM.
Yeah.
Who's working on it?
It was a research project by, I forgot his name. I mean, if you search for it on
Oh,
on
okay,
Google,
yeah.
you'll be able to find it.
Okay, that's interesting.
Because it becomes harder for a programmer to program, you know what I mean? For, okay, how am I going to get all these games out of,
Right.
you know?
Yeah, I think you'll see a lot of those suggestions and things in the talk today too. I think I'll cover those parts a little bit, and I think you can chime in there and have more questions at that point. And I think we can talk more. So that's good. So I guess I'll go ahead and start. They're probably walking. So the topic today I'm going to talk about is CPU versus GPU when their worlds collide. So it's kind of fun, I guess. So my name is Jayanth, and I work with AMD right now. But one thing I want to add as a disclaimer right off before I start the talk is that these are all my own personal views and nothing to do with AMD. So if you quote me on AMD, I might get fired. So I'm just going to just say, shh, because these are just my views. Okay, so I guess before I wasn't sure what the background of people around is, because one of the things that I heard were there'll be a lot of freshmen and others who have probably just started programming. So there'll be a couple of slides which are probably very basic. So I apologize for those who already are very well versed in the field. But anyway, so what are CPUs and GPUs? So CPUs are essentially central processing units. So basically when you write a program and they get decomposed into instructions at some point, like add and subtract and so on, that finally execute on your computers, the brain that actually carries out all these instructions on your computer, whether it's a laptop or desktop or whatever it is, is essentially what your CPU is all about. So examples of some of the manufacturers of CPUs are AMD, Intel, and so on. I'm sure you've heard these names before. And on the other side, there are these graphics processing units. So what are graphics processing units? These are basically just a specialized processor. What it does is it tries to offload the task of like showing off graphics on your desktop or laptop onto the CPU offloads it off into a separate device, and that device is what is called a graphics processing unit or a GPU. Some of the examples of GPUs are AMD, again, has a GPU. It's ATI used to be the GPU, and AMD acquired this company, so it's officially, when I refer to ATI somewhere in the talk, it's going to be AMD GPU. And NVIDIA is one more example. Intel has a lot of graphics processors as well. So with this in mind, so what are the main goals of this talk? So I think I mainly wanted to give you guys a flavor of how the CPU and GPU things are evolving in the industry, and show you what are the interesting trends that have happened before and what's going to happen probably in the next few years, so that you can start thinking about this area a little more. And then one of the interesting things which he brought it up out here in terms of programming them is the next big challenge for a lot of these types of devices. So I'm just going to touch upon them, and then I guess you guys should go and read up more if you are interested in that. And then the hope is that at the end of the day, I'll get you more excited about this whole area, the whole area of computing, so that you can take it up in your grad school or job or whatever it is that you go for next. So the outline is I'm just going to talk about the evolution of CPUs over the past few years. It's going to be a brief one, don't doze off. Then the next one is GPU, and then how GPU and CPU are kind of converging, and then what are the interesting challenges and opportunities in this area moving forward. So I guess anyone here has taken architecture class at any point knows these like simple pipelines. So how many of you are familiar with pipelines? Oh, okay, great, sizable number of you. So it's like a fetch, decode, execute, memory write back is like a typical one that you study in school, which is essentially like when you break down your program, we talked about it in the instructions, like an add, for example. You need to fetch this instruction from memory and execute, decode it, and then execute it, and then the results are written back to memory, and so on. So these are the different stages of a typical execution of a pipeline. So for brevity, I'm just going to put it as F, T, E, and W out here as these different stages. So you probably have studied about these pipelining effects, where the idea of breaking it down into stages is that you can actually, at the end of the day, while you're fetching one instruction, you can be decoding the other instruction in parallel out here. So if it's a 5-stage pipeline, at the end of the day, you probably have like like these 5 stages happening in parallel for different instructions. Like you have an add going in parallel with a subtract, with a memory instruction like a load and so on. So this is like a high-level picture of what you guys have probably studied in school. So when you look at it in the real world, it comes out to be something more like this. So this is like one of the modern CPUs from AMD. It's a Volume 4. So actually there's this fetch stage out here. Then there is this decode stage. Then these are the execute stages, which are like the floating point execution and integer execution units. And then there is this memory stage where you potentially write it back to the D-cache and so on. And then there's this write back phase pretty much encompassed out there. So just to give you a feel, this is what you'll probably see in the industry. And there's a lot of these complicated units, but the basic principles are extremely simple and same. So this would give you a good feel for what you should do like if you're in the industry. There are a lot of other units here like branch prediction and so on, which I won't touch upon in this talk. So they're all just remember that it's a pretty complicated piece of software when you talk about these AMD CPUs and Intel CPUs and so on. So this is like kind of the early evolution of the CPU curve. So what happened was that most of the complexity went into how to make these cores faster and faster every generation. So there are 2 things that probably many things that led to these things, but I'll just talk about 2 important aspects of it. One is that it became noticed that every generation these cores got more and more complicated. So these fetch, decode, execute, memory, write back stage that you saw was probably the very initial pipelines that kind of came out. With time, they became more and more complicated, and now in these chips, they have all these, as you saw in the previous slide, you have branch predictors, you have multiple stages happening in parallel and whatnot. So that's one trend that has happened. The second one is out here in this figure that I've shown in terms of frequencies. You don't need to know the exact numbers, but I guess it gives you a rough picture out here. Both AMD and Intel, the wars were mainly between these 2 big companies where to see who could produce like a faster chip in terms of higher clock frequency. So basically you must have heard of like 2 gigahertz processor versus 2.5 or 3 gigahertz processor and so on. The idea was that you take the same application, and if you run it on a processor that has higher clock frequency, hopefully it'll run much faster because it's kind of chugging on these instructions at a much faster rate. So over a period of time, so as you can see around until 2005, that was kind of the 2004, 2005, that was the trend where they were trying to increase the processing speed. So you've heard of probably even 3 gigahertz and 3.5 gigahertz processors that kind of came out. So the main problem that happened with this was that along with the frequency, the power went up quite drastically in all these systems. And so if you actually continue down this path of increasing the frequency, one thing they realized was it would lead to something like this, which is probably what you don't want to happen. So that's the time that people decided, okay, fine, it's now important to now stop these wars and talk about more at the granularity of what people want. Like if people want to run multiple applications at the same time, they don't care about whether each application is running fast. They probably care about whether these applications are running in parallel very well and so on. So that's what led to this, I would call it one of the fundamental transformations of the whole CPU world, which is where you came up with these, like, instead of having just one core out here, actually there are like 2 cores sitting next to each other on the same chip. So then, so in 2006, around that it came out, and then in 2008 you had 4, 9, about 6, 2010 about 8, and what next? So I think this is a question mark, I think which we'll probably talk about a little bit later, but it's not related exactly to CPUs. But so this has been the general trend of evolution of single core to multi-core processors on the CPU side. So with this, let's just hit upon what on the GPU side how things are playing out. So on the GPU side, over the last 20 to 30 years, if you look at it, it was simple like wireframe rendering kind of processors that were just doing some kind of wireframe rendering, and then with time they started having these like shading, depth buffering, and vertex lighting, and so on. So I'm not sure if it's very clear, but if you see in this figure, you can actually see its shadow, and then some parts are more have more light than the other parts, and so on. So it's basically these kinds of effects were added in this time frame. And then they had, you can see in the next phase, that was more like these textures. You can actually see these objects with textures. Here it's pretty plain. Here they have textures. And then this is where there's an interesting phase that started coming out, in that until now, there were these specific units on this GPU, on the graphics processors, which was actually doing these respective jobs of doing the vertex processing or pixel processing and so on. But at this point in time, they started having these things where they could actually program them to actually do any kind of shading. So it transformed from a fixed function unit, as we call it, into a more programmable processor at this stage. And moving forward, so this whole GPU, instead of viewing it as purely a graphics machine, it started being viewed as a parallel computing machine. So that's one of the big transformations that happened in 2000. So this is again a simple architecture of the GPU core. I'm not going to go into details anything out here. I just want to mention couple of quick things here. That here, as you can see, the pipeline kind of out here, like get the input, do some rasterization, and produce the output, and so on, is a typical a graphics pipeline where you have to render something on your screen. And these are the cores that actually do all the computation for each pixel. You need to do something to put it up on your laptop or your desktop. So these are the cores that actually do it. So these are the units that are getting more and more programmable. So these are the ones that actually have your heart of your computation. And so you can actually program them instead of doing graphics things to do other stuff. So this is where I want to introduce, actually I think it's easier to view this from the architecture point of view, and then I'll introduce a term called GPGPU beyond that. So, so we saw for CPU, for example, for a 4-core processor, you have like these 4 cores, right? And correspondingly, if you look at a GPU, you can think of it as having, here I have like 14 multi-processors, where each of them have 32 cores. So you imagine these cores are actually heavyweight cores that we talked about. They have like all kinds of branch prediction unit and extraneous complex cores. The idea of going to the GPU was because all it needs to do is simple processing for graphics rendering purposes. The hope was that these simple pipelines that are there, which you can basically you can put them out here. So there are like you replicate them, and so you have like simple pipelines, but many of them that are happening in parallel. So that's the way to, if you view GPUs that way, then it becomes essentially a multi-processor for actually doing a lot of things in parallel at the same time. So this is the time I want to introduce this term called GPGPU, that's which is general purpose computation on GPU. So until now, graphics processor was more like a graphics rendering engine, but now it's more becoming more and more a general purpose processor for running some high performance computing applications. So these are some of the, just to give you, this is just a slide to give you a fair idea as to what the differential in performance between these two kinds of devices because of these architecture decisions are. So on the y-axis here you see flops, which is number of floating point instructions that are performed per second, and this is for different years. This has been the growth. As you can see, the GPU around 2007 was about 300 something gigaflops, whereas CPUs correspondingly was about 50 gigaflops. If you look at the numbers right now, it's actually GPUs are over teraflops right now. It's like 2 teraflop chips you can easily get. Whereas CPUs, because of their multi-core, it's actually going slightly higher as well, and you'll probably see a little more extension out here. There's one more aspect of the CPU I didn't talk about, which I don't want to get into too much, but it's like the CPUs also have this other specialized unit called SSC units. I don't know if you're familiar with it. So these are like your floating point unit vector unit which enables you to run some small length vector things in parallel. So that width out there is basically increasing. So you're basically putting more and more functional units within a core as well. That's one more trend CPU is seeing. So both these together would contribute this to go a little higher, faster, but still this differential is going to be still maintained because that's the way graphics chips are built, and it's every year that they are built in, for more and more performance. So I think this is the time I'd like to show, if possible, demo as to where graphics has come to right now. Okay. Hope it works. So this is just showing the details as to which the graphics can actually render right now.
Is that real-time rendering? Is it rendering?
It's not rendering right now.
No.
Yeah, it goes real time when it goes down in the demo, yes. Not in this mighty fun. So basically what you see is that whatever is in focus is actually given a lot of attention, and then the rest of it is kind of blurred out. This is the ladybug. So I think this is this kind of area where they're trying to do this. It's called depth of field, where depending on the depth they want to have showcase different aspects of it. So this is one more active area of work on the graphics side. So I had to have it for a little bit. Yeah, the lighting differences are amazing, as you can see out here. I think that one of the hardest parts to actually do it right is the hair, because it's like moves everywhere. So here they have just a couple of them out here. Okay, so basically what you saw was high definition graphics rendering, and one of the directions that it's all moving to next is, you want dynamics, as in, you want to bring more and more realism to this whole, the whole aspect of rendering. And that would mean that it's not just going to be what it is right now, it's going to be like a lot of physical phenomena that needs to be integrated with the rest of the things. Like, let's say if the car here is going, I don't know, if it's going to run on water there, how the splashing happens, what are the effects, where does the water fly from there, and so on. So that's becoming the new big thing, and those kinds of things actually we'll talk about a little bit, is that those kinds of things are getting offloaded off to the GPU to do it in a much faster manner compared to the CPU. So this is one more side which of the GPGPU thing, which is interesting to note, is like it's being used in protein folding kind of simulations. So this is the work that's being done at Stanford right now, for example, where they're trying to figure out how to simulate the whole protein folding. The idea is that if you can find out proteins that are not folded properly, the misfolded basically, you can basically identify Alzheimer's, and then you can identify the kind of drugs that would actually probably go and, like which structures it's going to go and attach to. So you would build the corresponding drug based on how you would simulate the effects and so on. So the interesting thing though to note here is that if you run this application on the GPU, because this is essentially a molecular dynamics problem wherein you have these molecules that collide with each other and then move away and stuff like that. So it's an n-body problem, and these kinds of problems are actually embarrassingly parallel. So they are ideally suited for the GPU. So when you run these kinds of applications on the GPU versus CPU today, it's about I think this was a few years back, but anyway, so it's probably a similar ratio, a little better right now for the GPU. It's about 40x faster. So given that it's 40 times faster, the thing that you could actually do it in like 3 years in a typical simulation framework, you can actually do it now in a month. And this is probably going to get even better in the future. And so the whole GPGPU computing for these kinds of things has been a big boon. The other example of applications are face recognition kind of a thing, with I guess a lot of you are play around with Facebook and all that stuff. So right now it's, the CPU can do a little bit of face recognition, but I guess if you want to, like recognize with thousands and thousands of pictures and within a matter of few seconds and whatnot, GPUs are probably a better place to do it. So there are actually, even today while I speak, there are like algorithms being developed as to how to do these recognition on the GPU as compared to the CPU. This is one more example of this physical phenomena that I told about, where here you see like a rolling rolling ball that actually goes and displaces all these pins, so that the effect as to where exactly it goes and so on. It's a lot of physical phenomena that needs to be modeled. And again, GPUs here are probably going to be the right place to do a lot of these things. So now that I've kind of motivated what the GPGPU model is and what kind of things would probably fit into that, one of the things that I have to step back and tell you again is that even though it looks cool, the programming them is a nightmare. So you need to, yeah, it's that big a nightmare. Yeah, so you need to figure out, it's a processor that is meant for graphics to begin with, and you're trying to somehow use it for this multi-processor, basically multi-processing. And so that, so if you're going to write a program today that you run on your laptop in a CPU, if you try to run it on the GPU, nothing is going to happen. Nothing's going to come out of it because it's not meant to give you anything. Because it's a single core there, as you saw earlier, is like a simplistic core compared to the CPU core. So it will probably perform worse. So the idea is therefore to from the very beginning, start thinking about structuring your application in parallel. And that's where I guess your parallel processing classes here is going to be something that is getting pushed up higher and higher to like probably even the first year right now, because this is becoming the fundamental building block for the future processors. So I'm just going to give you a simple example of how a programming model is and so on. So I'm not going into too many details, just to give you a flavor. So some of the interesting GPGPU languages are OpenCL and CUDA. OpenCL is actually one of the industry standard right now. It started off a couple years back, and it's being accepted as a norm for many of these companies. And CUDA was started by NVIDIA a few years back. They were the initial, one of the initial people that started off this whole GPGPU computing efforts. So the idea is that you declare something called a domain. A domain is like an n-dimensional computation, like an array, for example. Let's say you have a matrix. It's a two-dimensional set of elements. So in that case, it's a two-dimensional computation domain. And on each element, let's say you want to perform some operation. So, and you want to define that operation using a computation kernel. Like, for that one element, you want to take a sine of it, cosine of it, take a log of it, and so on, and do whatnot for it, and and perform all kinds of operations which take a long time on the CPU. So, to execute a kernel on each point. So that's where like GPGPU languages kind of come into play, and they tell you, okay, so instead of structuring your application this way here, which is have a simple application where all it does is it takes in like two arrays, A and B, which is one dimension, multiplies them and puts it in a third array, C. So instead of doing it this way, which you would do it in a typical CPU, you would actually need to structure it this way, wherein you would actually say, okay, this is a computation kernel that you need to parallelize, and then so on each element, this is what is going to happen. So each element is going to go in, it's going to get its own global ID. It's essentially its position in that whole array, and then it's going to say, okay, this is my position. So given this is my position, I'm going to take in these corresponding elements from these arrays, multiply them, and put them in the final in the array C. So as long as all these elements are doing it in parallel, so you can imagine instead of taking n times basically out here, it takes like order 1 time out here because it does it immediately. So I guess this is the high-level picture of how you would write an application in like an OpenCL, the corresponding kernel. I think at this point I want to introduce what's called the execution model of the whole process. So how does it actually work? So the CPU, right, in this case, decides that, oh, okay, I want to take this kernel, which is essentially the compute kernel, and I want to run it on the GPU. So what I'm supposed to do is to actually send it off over this bus interface out here, which is called PCIe, to this GPU device. The GPU device in turn gets the data and the instructions as to what to do with this piece of computation. And what it does is, as you know, as I talked about earlier, these cores are actually massively parallel set of functional units. So what happens is they get executed out there, and then the final result is actually sent back over the PCIe to the CPU memory, and the CPU gets it back from there. So this is like the flow. So it's important to note the flow because it kind of gives you the flavor of how I would say the driver application corresponding to that would be written. Like right now, what you saw was a kernel which needs to be offloaded, right? So that is one part of the whole program. The other part of the program is all about how you actually package it into these data buffers. How do you actually send it to the device? How does it get computed and comes back? So it's basically an accelerator kind of an approach. So next, let me move on to, okay, I think given that I have, okay. I want to talk about two things. I'm not sure, I think I'll probably skip these two slides out here, which, okay, so let me just mention it briefly though. So if you have, so let's say you have the CPU and GPU right now, we know they are at two different ends of the spectrum, right? One of them is a highly sequential kind of processor, the other side is a highly parallel kind of processor. So in the industry, they felt, okay, there are different approaches by which we can try and put them together. One approach is to try and build a hybrid processor that has, both components to it. Like, why not build just one processor that can do both CPU and GPU? So that's the approach that Intel took in what's called the Larrabee. And for good reasons, I'm not going to go too much into detail with all this. All I'm going to say is that it kind of failed, that approach, for a lot of reasons. One of the main things was that along with the benefits that it came with being able to do both at the same time, it also came with all the drawbacks, so to speak, of these two approaches. So I don't want to diss Intel out here, so I just want to move on to something which is a little more interesting as to. So what happened at the end of the day was they said, okay, instead of trying to mix the two into just one architecture, let's try to have both these architectures around at the same time, but let us try and get them closer together. Let us try and fuse them into a single core, so that they can talk to each other really fast and do a lot of computation. So that's where these fused systems come into play. Like AMD has come out with this Fusion processor, and then Intel came out with its Sandy Bridge. So this laptop that you see out here is actually one of the first Fusion cores that have come out. So it actually has the integrated CPU and GPU on the same core out here, and so it's actually pretty neat. So at the high level, at the architecture level, what does Fusion mean? It means that on the same chip, basically, you put both the CPU and GPU cores. They have their cache hierarchy, they have these buffers, and then there is this memory controller which you talk to the same memory. It actually, if you go to details, GPU has its own memory. So now you're trying to have like one memory for both of them, and so you need to just play around with this. So that way, they're like more tightly integrated. So you can imagine this says, oh, take this pointer out here and from there execute. And GPU says, oh, okay, fine. I don't need any transfer of data. I have my data right there. So let me just start executing right away. So this reduces the whole latency lag between sending the work and getting the results back and all that stuff. And this, and so moving forward, we'll probably see a lot of these kinds of chips coming out. And the other interesting thing is, I didn't go into too much about power, but GPUs, when it comes to simple computation, I guess GPUs are much more power efficient compared to CPUs because they don't have all these complex units trying to do all kinds of computation. So at the end of the day, so if you can actually have something that chooses which one to run the application on, you would probably get a really good power performance solution. Right. So this is a marketing slide. I apologize, but I guess, so what are the main benefits of Fusion system? So at the end of the day, GPU have this throughput. GPU, as I talked about, is highly throughput optimized solution, like many things running in parallel. It's very good for high computation density, and it's really good for high bandwidth kind of things that need a lot of bandwidth. And on the CPU side, if you want compute quality, like if you want to do like more complicated operations and instead of float, if you want to work on doubles and so on, CPUs are much better. And it's also really good for fine-grained computation and for sequential optimization and so on. So these are obviously its negative sides, that the positives of one are negative of the other. The hope is that with a Fusion system, you probably get all these things, which is like value, power, and hybrid computation. So basically, as you can see, they're like far away from each other. They're kind of getting integrated, and then slowly they're all one. So everybody lives happily ever after that. So I think I'll now move on to some interesting challenges and opportunities when it comes to this whole area. I'll just briefly, I'll not try and bore you, but I want to just give you a high level of couple of slides about the work I'm doing, so it gives you a flavor of what kind of interesting research and product work is going on in the industry. So one of the things that you saw was the GPGPU execution model. Like, you just say CPUs are good at sequential, GPUs are good at parallel execution. So I think one of the things to think about is that both CPUs and GPUs are evolving, and they're going to get, they're getting closer to each other in some ways. Like GPU is getting more programmable on one side. On the other side, CPU is also getting more of these vector units I talked about briefly before, and more cores. So with these things, what will happen is that you at the end of the day, you want to have something, a model that says, okay, these are the kind of devices that you have, and then you want to try and utilize the devices as best as you can, given an application, instead of thinking about, oh, okay, this would run good on the CPU, run it on the CPU. This would run good on the GPU, so run it on the GPU. So instead of the application programmer determining all this stuff, we want to have a way by which you automatically figure out, based on the application that you write, where to run what. So in that case, CPUs is no longer a control node. It will become, it's a full partner execution node at that point. So I guess just to show, just to motivate this a little further, here is like if you look at a high level, CPU and GPU architectures. So both of them have some kinds of cores, and they have some kind of cache hierarchy, and then they're connected to the memories. So if you actually look a little deeper, CPUs have these SSC or functional units, and GPUs have these these huge set of processing elements running in parallel. So so the idea is then to actually, I don't want to go into these details out here about the kind of memories it has and stuff. So we came up with a way by which you can actually map all these memories and whatnot of the GPU on, somehow there's a kind of correspondence. This local memory maps to the cache out here. These private memories map to the register file, and so on. So once we made this kind of a mapping, then we could actually we are in a position now to actually solve this kind of a problem. Basically, the idea is you have these physics simulations, image processing, and other applications that you saw earlier, and then you have these heterogeneous systems that have CPUs and GPUs. I think this goes back to VM that you were talking about. So the idea is to actually come up with this layer that kind of sits between the two. This is the whole software system that would take these applications and say, oh, okay, which one is a better place to run my application on for this part of the code, and then run it there, and then run the other part out there. Some of the initial results are published in this conference out here, and I think there is a lot of interesting work moving forward in this area, because you don't want I think at the end of the day, you want the applications to be simple, and you want most of the complexity of figuring out which device to send and everything to be hidden somewhere in the software layers. So that's one of the interesting areas of research, I would say. So I think that would be a good starting point to even visualize some of the other work that's going on. So for example, this is the Stanford Pervasive Parallelism Lab. They are doing a lot of this kind of work as well. So on the hardware side, they're kind of dealing with all these kind of different types of cores, these SIMD cores, out-of-order cores. So these are basically CPUs and GPUs kind of stuff. And then these are the layers that they're trying to come up with, these runtime systems that would basically kind of map to different kinds of devices. The other interesting thing that's happening is that they are trying to come up with these things called domain-specific languages. So instead of having like one language like C or Java or anything that would actually people want to write in, why not have like one language per domain? It's not going to be as much a language as in it's not like going to be another C or Java or something like that. It'll probably be based on one of the existing syntax. Will probably be one of the existing languages, but they'll have more like more libraries corresponding to that particular language. So they'll have some enforcements. Okay, so for example, if you're going to do something like a physics simulation, then one of the things that is probably going to be really useful is to have matrix multiplication all the time, right? So what would you do? You, instead of having somebody to say add two matrices and then multiplication and stuff, you probably have like a library called does matrix multiply, something like that. So once you have these kinds of constructs in these languages, you can imagine these lower structures out here to be able to understand what they can do with it to best. Like if matrix multiply, it knows how to spread the matrices between these different devices, and then do it in the best possible manner, as opposed to trying to do it, as opposed to having the application writer figure out which part goes where and so on. So this is one more thing I would definitely recommend you guys go take a look, because this is they're coming up with a lot of these different they're called DSLs, the domain-specific languages, and it's based on the Java framework. So it would be an interesting starting point to get a feel for where this kind of research is going. One of the other main trends I wanted to give you a quick heads up was about this whole thing is kind of moving towards, there are two things, as you all know, things are moving towards. One is mobile computing in terms of laptops and tablets that you guys are carrying around, and on the other side is like cloud computing, when you have Facebooks and like MySpaces and whatnot, where most of the data is actually present on the cloud. Sorry. Yeah.
What's better for mobile phones, GPUs or CPUs?
Mobile phones actually, they need some part of the graphics component for actually showing off the graphics side of stuff, but you don't need really complex ones because you don't do a lot of processing there. On the CPU side, again, you need really simple cores because you don't do a lot of processing again. So a lot of these, so we talked about ARM as one of the companies that does that. For example, your iPhone has this ARM processor, which is a really simplistic CPU kind of code. It's really simple GPU code. So when you have these kinds of things, so I think with time though, even these processors that are there, they're actually getting multi-core and so on. So the hope is that, I think that I'm going to touch upon this out here too, is that this whole notion of thin clients, right? You want to have your client, which is essentially what you hold in your hand, as thin as possible, so that you don't have to, because it doesn't have to drain too much power and whatnot. You want to keep it as, you want to have it as much battery life. That's what you kind of target. But a lot of the computation then should actually move to the server side. So that is, you say, okay, I want to recognize these faces or something like that. That's the command that the cell phone should send. And at the server end, you have like thousands of photos and everything stored, millions of photos stored, and a picture that you just send once will actually get, like computed at the background, and then you send back, okay, these are the links for which was a match, for example, and so on. So that kind of computation is going to be really popular. Here I was, when I meant mobile, I was talking a little bit more on the laptop and tablet side of things, mainly because it's, again, I'm talking about CPUs and GPUs, which are a little more on the complicated cores. So on the server side, you would have these kinds of specialized, like these fusion cores, or you would have CPU and GPU cores that are actually going to do a lot of these computations. And on the front end, you'll have these low power devices that we talked about. In the case of cloud companies, like this is one more major trend in terms of like there is Facebook and others have so much amount of data, and you have the other examples are like there are so many websites, and there is so much amount of sensitive data, like your traffic signals and whatnot. You have the sensor information. It's all huge amounts of data. You want to find ways to optimally get the right, get the right amount of data from these different, to access the right data, to analyze it and come up with all kinds of stuff. So again, this is all happening at the back end, basically. So this distributed and parallel computing is one of the main areas which is evolving, and so this is the next logical step of evolution. A lot of the things I talked about. So I think I'll just end this talk with saying a few things. One is that the CPUs and GPUs, their worlds are colliding, and note that they're actually pretty complementary to each other. So kind of putting them together makes it a really interesting, chip to play with when you want to do a lot of fine-grained communication between them and whatnot. The major problem is going to be on the programming side. So I think one of the software people, when this first came out, they said, oh, all the hardware people are doing is kind of screwing us more and more every year. So this is pretty much one of the important reasons why you need to think more about what programming models to use and how to actually kind of do it in the best possible way. And yes, software is going to be one of the major focus, especially when you guys graduate and so on. And this move towards mobile and cloud is obvious, and everybody needs to, I guess, cater their products both in terms of where they want to do research in and where they have companies do their products in these spaces. And it's a very dynamic field, and there are a lot of interesting problems to solve. So it's a very systems area, so I would highly encourage you to take a look at it and spend more time kind of do research on that. Thank you.
We have time for a couple of questions.
Yeah.
How come GPUs are so much better at handling physics and CPUs?
Right. So physics, again, when you talk about things like, again, I think I shouldn't say for all physics computation GPUs are better. Think of it this way, right? Let's say you have an n-body, let's say you have particles that are colliding with each other, right? And then you have these, I don't know, van der Waals forces and whatnot. That's like 1 upon square root of R2 minus R1's whole square and all that stuff, right? So it's a big complicated mathematical equation. Now, GPUs have some, on one side they have some specialized units, like I think they have some square root unit or something like that does these things like in a jiffy. And then the other side of thing is that they have so many, and if you have like if the number of particles you have is like on the order of millions that are colliding with each other, you have these so many units that are out there, which can each kind of process like 2 at a time. And that way, on the CPU, on the other hand, there are just like, like 4 cores that can try to do something. On GPU, there are like hundreds or thousands of cores that can actually try to do this very fast. So both these things kind of make it a really good option. But on the other hand, like there could be some physics computations which have like, which are really complicated, which are like, if something happens, then do this. If something else happens, then do that. Then if you tell the GPU to do it, it's going to be like, okay, I give up. I'm going to be slower than the CPU. So it all comes down to the type of application. And that's why I think this whole middle layer of software I'm talking about is so important, because in that case you could look at the application a little bit and say, oh, okay, this is probably a better fit for the CPU, not for the GPU. So why not just run it on the CPU, and so on. So, yeah.
Is AMD's graphics division still in Canada, or is that?
Yeah. So actually, I kind of work in the graphics division, even though I'm a CPU person in this company out here. So they have and Toronto is one of their centers. The next big center. Well, actually this is the main center, I would say, because this is where all the execs are. So the Sunnyvale center. So it has a lot of graphics people there.
Okay.
Yeah, and they are constantly hiring. So.
Okay.
Yeah.
What are the performance increases do you see by adding more cache to the chip? And as the wires that get longer and longer, is there some type of physical, limit that there's not going to be an ability to add more cache to a chip, and then, now you're going to have to go out of the processor? So it's two parts.
Okay.
Like how much performance are you going to get if you're going to be able to take that slow RAM and put it on the die and make these operations faster, grabbing.
Right. So on one side, I think you're talking about the increase in cache size, like L2 and L3. Is that what you're talking about?
Yeah, exactly.
Right. So I think the whole idea of caching is twofold, right? One is that you want to stop it from going outside the chip as much as possible. Try to capture a lot of these things. And the main places where you can capture things are where the applications have a lot of locality, whether in terms of spatial or temporal locality. So now the benefit of adding caches comes down to the type of applications at the end of the day that you run. So if you're going to run applications that are just like streaming in and streaming out, like you want to have like a big video that streams in, you do something to it, and you just write it out. There's no like reuse of any kind. So caching is just like you might either just have some buffers that just as long as they have enough buffer space to hold on this, well, you can send it back. That's good enough. So the cache size then may not matter as much. But on the other hand, if you're going to do some sign up graphs applications and so on, where you're going to have these like vertices that you're going to reuse for the next computation and so on, then these caches play a very big role. And so definitely the cache sizes, that's why, especially for running on your CPUs, you'll continue to see probably some increase. Like you already have like 2 MB, 4 MB caches, I guess, on that side. So that's going to happen. Yeah.
Last question. So do you guys have anything like that competes with NVIDIA's like Tesla? Because I was at supercomputing and it seemed like they were more on the supercomputing side.
Oh yeah. Okay. So I think one of the things that's Tesla is the workstation chip, I guess, from their side.
Right.
So I think there is an emphasis on that workstation side that's going on right now at AMD as well. So you'll probably see more of it. I think conventionally, if you look at the processors themselves, I think I don't know. I don't want to sound biased, but at least apparently every year one company produces chips that are much faster than the others, and so on.
Right.
So like 2 years back it was NVIDIA, last year it was AMD did that, and this year who knows.
Right.
So given that is the case, so that's only one part of the whole solution. The tougher problem is to do with software for these. And so NVIDIA has a head start in terms of its CUDA that it started off with. And so that's why in the server market, so it's very important for like AMD to compete very well to first of all make OpenCL, which is what it has adopted to be used more, and first of all, and secondly make these chips and target towards that.